In this screencast, I'll talk about some of the underlying principles of radiation and define some of the terms that encompass this mode of heat transfer. So there are four distinct radiative heat fluxes, and these contribute to radiation heat transfer. So the first one, E, is what's known as the emissive power. Then we have G, which is termed irradiation. J is the radiosity. And finally, what we're probably looking for is Q, which is the net radiative heat flux leaving the surface. This can be defined as J, the radiosity, minus G, which is the irradiation. So let's take a look at these different terms and see how they contribute to radiation. So the first one is the emissive power, E. And emissive power is the rate at which radiation is emitted from the surface. The easiest way is to treat a surface as a black body. And what that means is that, therefore, all the incident radiation is absorbed. In addition, it emits the highest energy that can possibly be emitted from that surface. And finally, our radiation is independent or not a function of direction. If it's a black body, we call it E sub B, and it can be calculated as sigma T to the fourth. So the sigma is known as the Stefan-Boltzmann constant, and our T is the temperature of the surface that it's emitting from, and it is measured in Kelvin. However, if we have something that isn't a black body, then the emission is going to be less than that. If we look at emission from a real surface, now this is equal to epsilon then E sub B. And that epsilon is what's known as the emissivity. This can range from 0.02 for highly polished metals, technically all the way to 1. So we can look at the emissivity as a correction factor from a black body to a real surface. One of the more complicated radiative heat flux is the irradiation. Irradiation is the rate at which radiation is incident upon a surface. So what that means is that it can be transmitted, it can be absorbed, and or it can be reflected. And we use the symbols tau, alpha, and rho to denote the fraction of that irradiation that is either transmitted, absorbed, or reflected. And since irradiation has to be one of the three of those, or all of them, we know that this tau plus our alpha plus our rho has to equal 1. Now we can simplify this by defining what's known as an opaque surface, and that means that there's no transmission. So rho plus alpha is going to equal 1. So next we'll talk about our radiosity, J, and this encompasses all the radiation that leaves the surface. Certainly, one part of it is going to be that emissive part. So this can equal E plus G. So let's look at some examples of situations where we can calculate the net flux. So the simplest case, as I mentioned before, is a black body, and here the energy leaves the surface only as a result of the emissive power, and all incident radiation is absorbed. Therefore, the radiosity equals the emissive power, our emissivity is equal to 1, and our radiosity is just equal to sigma T to the fourth. A second example is an opaque, diffuse gray surface. And so what does that mean? Well, we'll start with opaque. Opaque means that, again, there's nothing that's transmitted. Diffuse means that rho and alpha are not a function of direction. And gray means that nothing is a function of wavelength. In subsequent screencasts, we will be able to take these ideas and show how to calculate the net heat transfer from an opaque, gray, and diffuse surface, and then look at radiation to surfaces within an enclosure.